Warm welcome here from Switzerland. Good morning, America. Good evening, Europe. Welcome to this Kistler webinar on acoustic emission, practical consideration and condition monitoring. I'm glad you followed our invite. My name is Pascal Erne and I'm working for the test and measurement team at Kistler. Please be aware that today's webinar is recorded and that you're muted on purpose. The recording will be shared afterward with you. If you have any questions during the webinar, please feel free to use the Q&A section on the right-hand side. There is a box of your screen. So we will be happy to answer your question during the webinar or at the very end. And if we do not have enough time, for sure we'll come back to you via email or phone. And now I'm proud to introduce you to today's presenter, Bill Zwolinski. Bill holds a master's degree in electrical engineering, specializing in signal processing and controls. Before joining Kistler more than 20 years ago, he has worked in the field of underwater acoustic and was chief engineer for the Navier Carroll landing system at Textron. At Kistler, he's involved in all the challenging test and measurement applications and acts as an application engineer. With his enormous know-how in both the mechanical and the electrical world, he's heavily involved in solving our customers' measurement problems. And now we are all curious to learn more about the benefits of acoustic emission and what else is coming with this really interesting topic. Bill, the stage is yours.
Thank you, Pascal. Appreciate the introduction. Okay, so the agenda for today, I'm going to just minimize Pascal here so we can see. The introduction, we'll go through a bit of an introduction, what the principle of operation is. We're going to talk about mounting. Like in any sensor that we use, is always the best performance is always given by having the proper mounting. So I think we're going to really address that in good detail. So there's a clear understanding of how to mount the sensor to get the most out of it. Certainly, measuring chains include not only the sensor but cabling, the signal conditioning, and data acquisition nowadays is quite integrated with measurement. We'll go through a few applications and have a summary and wrap up, and then there'll be some time for Q&A at the end. So, just as a lead-in, I mean, the field of condition monitoring and preventative maintenance is one of the areas that we're addressing here today, and that is really trying to understand before a process or equipment fails, when it's say close to failure or pending failure is imminent, perhaps over a 60 or 90-day window. Obviously, if you can predict even longer ranges in advance, that's even better, because that gives the maintenance staff quite some time to properly schedule that and maintain good operating equipment. The field of rotating equipment often is considered with condition monitoring. Certainly, like pumps and fans and compressors and motors, all these have wear over time, and anyway, there's quite some cost involved if you don't detect problems in advance. And certainly the obvious conclusion is, oh well, you're not going to be producing materials. Well, that's one thing, but there's all kinds of other secondary things, such as late deliveries, customers being unhappy, losing business. I mean, all these are quite severe, if you really think about them. So in the whole, it really provides a means of managing your business, certainly, and avoiding any catastrophic failure. Anyway, acoustic emission is one of the measurands I'm going to address today, and I'll tell you a little about that. But fundamentally, in these applications I spoke of, it could be the oil and gas industry, petrochemical, hydropower, steam generation, boilers, nuclear power, and even cutting force areas, which propagates over many industries, from aerospace to universities to automotive and so forth. So there's a lot of different ways you can use acoustic emission to detect events such as pump cavitation, water turbine cavitations, leakages of all sorts, from valves and piping, seals and storage tanks. Fatigue and wear of bearings, for example, would also be an area. Loose part detection in nuclear, marine propulsion where you have prop shafts and rotating propellers, perhaps cavitating. Other areas that are also in consideration are in the cutting force area, where you're always trying to really optimize speeds and feeds and tool design and really trying to get the best performance out of your cutting regime. So in this area, acoustic emission provides a special insight that isn't obtained with any other measurand, actually. Certainly in terms of manufacturing processes and gas turbines, in terms of cracking of the blades and integrity of gas turbine operation is also an area of where acoustic emission does play a role. So acoustic emission, it's basically, it's an elastic wave generated by a release of energy within a material. So we call this a surface acoustic wave or a Rayleigh wave. And now this is somehow related to how materials in the stress and strain diagram I have to the right. It's very classical where you see quite a linear operation, stress versus strain, and then you see the nonlinear in the plastic deformation region where the material is being excessively stressed, and those areas are where you're really able to measure ultrasonic signatures that represent certain conditions of the material. And that's really what the AE, the acoustic emission sensor, is doing. It's allowing us to get advanced information on materials, how they're being affected by various processes, and that way we can use that information to better estimate failure or when they need to be maintained. Again, the surface acoustic wave is a very low intensity wave, but it's a very high frequency. So it's a 50 kilohertz to 1 megahertz. So it's not in the audible range. You're not listening to an acoustic emission signal. It's really it's the measurand is vibration insensitive, which really gives a powerful advantage in a high vibratory environment where a lot of industrial applications nowadays can be, you can have a lot of acoustic noise in that facility, a lot of structure-borne noise as well in terms of vibration as well. So being able to separate at a measurand from all this high vibratory environment is actually rather unique. And it's like I say, it's a special measurand that really provides some benefits in those types of environments. Sensitivity of AE sensors is typically referenced in dB, but dB reference to 1 volt per meter per second. So I'm going to give you an example in a bit like that, because a lot of times when people start talking dBs, a lot of people get a blank stare, and hopefully we can add some value to what that really means in the next few slides. But anyway, acoustic emission really is a relative measurement. So a lot of times what you're really trying to accomplish is you're saying, okay, what is the operation of my equipment when it's pristine, when it has no impact to it with any material defects or anything to do with material wear or so forth. Then you compare the performance as the equipment is used, as it creates certain anomalies or defects, and then you're able to detect them with the acoustic emission. So it's definitely a relative measurement, and certainly this vertical displacement of the surface wave that I talked about is exactly what the acoustic emission sensor measures. So what does this thing look like? Okay, it looks like I show you in the upper left-hand corner. It's basically a rectangular sensor, maybe about an inch or so long and maybe half an inch high. It's made of a piezo ceramic-based element, and it basically has a coupling, a diaphragm, if you will, that basically is at the bottom of the sensor, and that needs to be not only coupled to the surface, but also preloaded. You need to actually mechanically load it, and you do that through a screw, or there's other methods which I'll talk about briefly. The real, I think, interesting thing for these types of sensors is they're basically case isolated sensors, very rugged industrial sensors that can be used simply in laboratory environments, but basically in very harsh industrial conditions as well. Temperature ratings on up to 165 C and minus 55 C, and in a lot of the applications in the power and energy or energy and infrastructure segment, you often are in areas like in the oil and gas industry where explosive or hazardous environments exist, either all the time or maybe some of the time. So in those cases, you need to have certain classifications and certifications of the equipment, which is called ATEX or CSA approvals, and we'll talk about that a bit. But these sensors absolutely have that. And the way they're designed anyway is they have basically two basic frequency ranges, 50 kilohertz to 400 kilohertz, which has a higher sensitivity, and the broader band, the higher frequency band from 100 to 900 kilohertz has a lower sensitivity, but again, gives you reach out in the higher frequencies. And when we talk about frequency specs and these bandwidths, we typically say in accelerometers talk about a 5% bandwidth. Well, these are 10 dB bandwidths, so they're fairly broad in nature, and that's fairly common in this with this measurand in terms of acoustic emission. So I talked a little about the background here. Well, there's the calculation I'm giving you for the computing the reference sensitivity in dB or in volts per meter per second. You can see that the sensitivity reference is actually 1 volt per meter per second. And the actual formula is there's really the sensitivity of the sensor divided by the reference sensitivity. So what happens here is you get a 57 dB for the lower frequency range acoustic emission sensor and a 48 dB for the higher one, which I said earlier that it is a lower sensitivity. Well, you can easily relate that to something maybe more say meaningful to a lot of people. Is volts per meter per second is not on a logarithmic scale, but certainly gives you a feeling for what the sensitivity is over the operational range. When developing these sensors and when using these sensors, I mean, cabling is always the most important thing to a sensor in my view. I mean, I've seen just poor cables being used in various applications, and although the sensor is great, and you get poor results. So cabling, I think, is important, but with cabling, you not only have to provide an ability to withstand the operational environment, but you got temperature up to 165 C, and then obviously cables at higher frequencies are going to have some loss associated with them. So what you see here is really just the effect of loss of a cable with frequency and with temperature. So it gives you a flavor for the robustness of the design. And this is, not uncommon, where at higher temperatures you do see, more loss in the measuring chain. But again, the sensitivity of the sensor is quite high already, and that absolutely provides a very robust solution. So in terms of mounting, I mentioned the bolt. What the bolt will do is it'll basically allow you to preload this diaphragm into the test article, and or you can use a magnet. Okay, this magnet has a sufficient holding strength to fit over the sensor, but also this thumb screw basically pushes down on the sensor much like a bolt would. In a lot of applications, you're not able to really drill and tap a hole. So this is provided you have a magnetic structure around, you can easily use this. And there are, say, other derivatives of this concept which you can say epoxy down and still use this thumb screw press down on the sensor to preload it. So it's a very common technique to use either a screw mount or some sort of clamping method to push the sensor down into the test article. In terms of things to remember with mounting of acoustic sensors, the surface finish or the surface flatness or finish, I would say, is a parameter that you should take note of. Certainly, AE sensors are typically mounted to any hard and flat metallic surface, but any air gaps or loose surface or loose connections or soft materials will say degrade propagation. And I usually try to tell people if you're going through a lot of mechanical interfaces, you're going to have some signal loss per interface. And certainly, if any of those mechanical interfaces result in, say, loose surface couplings, you're going to further lose acoustic emission and much like an air gap, and then you'll have to find a better location in those. But surface or the location of the sensors important, but also the mounting surface and how you mount the sensor is also important. So what we're going to do here is take a look at a magnet versus screw, a ground surface versus a rough surface, and grease or no grease in the mounting. And grease is often used as a coupling agent to improve the mechanical coupling of a sensor to the surface. These are just some qualitative pictures of what you see. The bottom two curves are really a magnetic clamp without silicone grease on a rough surface, and it's usually with a screw, or the red is with a screw and the black is with a clamp. The next set of curves here, and you can see here, this is the relative signal strength here. So at this level here, when you have a rough surface with no grease, regardless of a clamp or screw, you're going to get the lowest signal strength. Now, if you use the same properties, but also now use silicone grease, you see a doubling of the signal from what you had previously. And then lastly, if you have a ground surface, you see a further improvement. And what you also see is that as you use a screw, the screw mounts are absolutely the most preferred in terms of overall signal quality and integrity of the measuring chain. And this is just a summary of those things. And we're going to hand out this presentation, by the way, for anyone who's interested. But again, screw mounting is the preferred one. Smooth surfaces are preferred over rough, and silicone grease are preferred over non-grease surfaces. Other things to keep in mind with AE signal quality is really the distance between the AE source and mounted AE sensor. I mean, the sensors are quite high in sensitivity, so you don't have to be right on top of it. But again, it is a parameter to keep in mind. Quality of the mounting surface we've already adjusted or addressed, and the power of the AE signal needed to make the measurement. So that's all sort of relative. But again, with a magnetic mount, what's really cool about using a magnetic mount is you can change the location of the sensor really easily and really find optimum locations. So it's not only for say ease of use, but also convenience of determining the mounting location. So how does this thing powered, and what does a measuring chain look like? Well, an AE sensor is typically, not unlike an accelerometer in terms of it's an IEPE style of sensor, but it's not operating like an accelerometer. I mean, its bandwidth is super huge, so you can't really use a traditional accelerometer power supply to power this. With that said, you use a power supply that's in this case a few volts in magnitude, and with a 4 milliamp supply, and you're able to realize a 2.5 volt bias plus or minus 2 volts on the signal internal to the coupler. The power supply coupler, at least we've used for these applications, really has a lot of flexibility in terms of setting the gains. Okay, you can have different gains from 1 to 1,000. Obviously, setting gains at higher gains amplifies both signal and noise. So you always want to be mindful of that. Certainly, the RMS time constant is also important. I'll show you some examples of where and how to judge, what time constant to use and on the RMS. And RMS is basically gonna give you basically the envelope of the signal, this high frequency signal. And then you obviously have either RMS output voltage or current, and you also have a raw AE output. But the actual raw AE output is very high frequency. So, there's not traditional or conventional equipment that interfaces with such high frequency signals. So you're going to need some high speed data acquisition if you're going to be using the raw AE output. And I'm going to talk about that shortly. There's also internal filtering, bandpass filtering that you can plug in, comprised of second order filtering, and you can create a bandpass filter. So what this system will do is it'll allow you to basically tailor the signal to the area of interest and be able to then detect AE and set a threshold to indicate that you've exceeded that threshold in this AE event that you want to detect. So pretty complete system, simple but effective. This is what it looks inside. I'm not going to go through this for your benefit, but basically inside the coupler are terminal blocks that you screw into. We supply ferrite chokes that really help attenuate any or any high frequency noise, and really give you a high fidelity signal on the output. What RMS refers to is really, if you look at the red signals, these are the live acoustic signals, AE signals, and the blue one is really the RMS output. I like to always refer to the RMS as like an envelope. It gives you the envelope of the signal. And what I mean by that is if you can see the red curve, you can see there's a lot of up and down varying content in there. But you can almost see that the blue curve sort of emulates the pattern of the peaks. You can see it peaks up here and goes down. Same thing here. This peaks up and goes down. Same thing here in this RMS. So by picking short or long RMS time constants, you can better tailor your output voltages to represent the detection of the AE event that's of interest, and that's often a very powerful tool. With regard to raw AE output, you're going to need sample rates on the order of like 5 to 10 megasamples per second, and with the RMS output, you can probably get away with 10 kilohertz or lower, which is very common with regard to a lot of data acquisition systems out there. So a lot of folks like to use the RMS output, but unfortunately, with the simplicity of that comes with a little extra work, and I'm going to talk about that a little bit later. So this is another illustration of what it might look like in terms of the AE signal. You've got a raw AE signal here, and then you have also the RMS riding on it. One is a short time constant, one is a long time constant, and you can see that the short time constant best represents the envelope of this raw AE signal. And you can see here that we need 5 to 10 megasamples per second data acquisition sample rate, and on the RMS output, you can get away with 10 to 20 kilosamples per second easily. And this is another illustration of that, but also what you see is there's a limit switch output of the coupler. So when you're doing condition monitoring, it's important to understand when you did exceed a certain preset threshold, and that gives you an indication that the failure did occur. I also want to mention, because I mentioned earlier filtering being an option. Well, whenever you filter, you always got to be careful not to filter too much. And what really the optimum scenario with regard to AE is that you're using the raw AE output, okay, this raw AE output, and you're going to a high-speed data acquisition system without any filtering, and you do digital filtering to really optimize, the solution. It's quicker, it's faster, and it gives you, I think a more precise result. When you're using a coupler and changing filters and doing these things manually, you could absolutely arrive at the same result, but it'll take you quite a bit longer. So there's always a bit of a compromise in how much investment time you want to make up front. And if a high-speed data acquisition system is available, it's often the best way to go. Okay, I talked a little bit about hazardous zones in terms of the energy and infrastructure, or power and energy segment. We talk in zones. I mean, zone 0 is a hazardous atmosphere, highly likely to be present, and zone 2 would be one that is not likely to be present. Maybe it's present only in a catastrophe or something fails. So in terms of what we're doing here is we're qualifying the actual components that go into these zones to operate without actually being a cause of igniting or causing a spark in the environment to create an explosion. So a lot of what you do in terms of hazardous zone ratings is ensure that the actual equipment in the area can't create a condition that creates an explosion. And that's quite severe, a lot of safety involved. So if you're in those types of atmospheres or those applications, there's definitely another layer of requirements that need to be solved. In terms of the couplers, I mean, the non-ATEX couplers are generally totally open and easily flexible, putting in different filters, changing values. Whereas since the zone 0 and zone 2 solutions don't require you to modify equipment in terms of these zones, you have basically you have fixed gains you select up front, you have fixed outputs, you have fixed time constants, and you're wide open. You're not doing any filtering. So the level of flexibility is reduced substantially for equipment going into a hazardous zone. With that said, I mean, there's also Zener barriers or Zener diode barriers. And what a barrier does is it limits energy supplied to a circuit to protect hazardous areas from excess energy. So it's much like what I just said to you, is that in the hazardous zone, in this hazardous zone applications, you're interested in not creating an explosion. So there's a lot of regulation or regulatory hurdles that you must meet in terms of the operation of your equipment. These barriers, by the way, there's two flavors. One will clamp at 13.7 volts and the other will clamp at 23.7 volts, depending on your application. Now, what's really cool is when you think about these barriers and you think about the application, you see, I talked about very high frequency up to almost 1 megahertz. There's a lot of barriers out in the market that basically do perform the same function, but are not capable on up to 1 megahertz. And what you see here is that, at 1,000 kilohertz, 1 megahertz, you're absolutely flat out. So the barrier is not distorting anything to do with your signal, where you use standard commercial barriers and their bandwidth is nowhere near what you need to really do an acoustic emission solution. So having the right barrier, especially for the raw AE output, is absolutely critical for operation. So just some scenarios here, just to take just 1 minute. If you're going to mount the coupler, the actual coupler, into the hazardous environment, then you can see here that in zone 0 you're going through several barriers in the safe area, again to protect the overall integrity of the measuring chain. Whereas if you're in zone 2, you simply need one barrier on the power supply. And this doesn't need to be this high frequency barrier. There's a lot of commercial barriers out there that will easily do the job there. On the other side, if you have the coupler in the safe area, now you could route the raw AE signal through a barrier like the 5252A1 that I just discussed, and basically get every benefit of using the raw AE to detect and to characterize the acoustic emission for whatever process you're monitoring. In zone 2, there's no need for that barrier. You could wire direct from the sensor to the coupler itself. So in terms of analysis, I would say, generally when I get calls and say, hey, Bill, I want to do an acoustic emission application, I always try to remind people that acoustic emission is very powerful, but there's usually an R&D effort associated with really implementing it. The reason why is, as I mentioned before, it's a relative measurand. Okay, so you're gonna measure what normal conditions would be in pristine environments, and then look at deviations of that to really assess what's bad and what's good. So you need to really investigate that and really look at what magnitudes of AE signals, where are you mounting the sensor, what frequencies are these AE events at, so you can better create detection criteria to support your condition monitoring solution. So again, that's very important. And again, a lot of times people are looking at waterfall plots or spectrograms, and I'll show you a few examples of that. And that's usually giving you time, frequency, and then an amplitude. It's either if it's a waterfall, it's typically a three-dimensional looking type plot, like you see here on the left with the red curve, or a spectrogram basically is a 2D plot with different colors signifying amplitudes or intensities and so forth. So FFT-based techniques are very common when you're doing AE analysis. So very much, I just want to restate, it's often very, very common to use a high-speed data acquisition system along with your raw AE signal to really converge on solutions quicker and really to get a reliable detection criteria that you can use for condition monitoring and preventative maintenance. So now we go into the data acquisition. Now, this is a company that we're quite familiar with, Elsys, and certainly we don't, Kistler isn't owning them. I'm just using them as an example, just to get an appreciation for what the capabilities are out there. I can tell you that back in the day, I mean, it used to be that the data acquisition systems were the weak link in measurement. And that maybe 20 years ago was the case. Nowadays, the sensor is usually, I'll say, the weak link to the data acquisition. Because data acquisition systems can have dynamic ranges of over 100 dB. And having any sensor, I don't care what type of measurand, that has 100 dB dynamic range is really a special sensor. So I let you keep that in mind, that nowadays there's such a wide choice of data acquisition. And certainly it's always good to find your favorite application engineer when you're trying to figure out what to use, because there's a lot of the devil's in the detail when it comes to data acquisition. What I like about certainly the Elsys system, it's capabilities on up to 240 megasamples per second, which is absolutely crazy that you can do such high-speed data acquisition. But certainly for acoustic emission in the 5 to 10 megasample per second range, simultaneously sampled channels, easily done, high fidelity from 14 to 16-bit resolution, so you're easily capturing 90 dB dynamic range, which again, it will easily satisfy your acoustic emission needs. A lot of times this equipment will trigger on events and only collect data for a certain amount of time. And that way, when you're collecting data at 5 and 10 megasamples per second, you don't need hundreds of terabytes of memory. You're capturing data for short periods of time, storing it away, and then analyzing it later. This is just a quick idea of what it might look like. With this Elsys system, pretty intuitive system. You have a raw AE signal in the green, and you have the RMS output in the red, which I showed you. And this is an FFT of that signal. And you can see here, I don't know, it's a logarithmic scale, but you can see somewhere around 50 kilohertz to 1 megahertz, you're seeing, quite a bit of signal energy. What we used here was just a simple pencil break test, which is fairly common to generate broadband acoustic excitations. And this is just another example of two different time constants. One is 0.12 millisecond, where you can see that the envelope really traces well the actual event you're measuring. So I would say the 0.12 millisecond is really quite optimal for this. Whereas if you take a 12 millisecond, it's actually almost, it is really no structure, really. I wouldn't use a 12 millisecond time constant, integration time constant for this application at all. So I wanted to throw this application is because this is a little bit using the ELSYS equipment, because they offer some neat features that I thought were pretty cool. So anyway, what we did was we did three scenarios. One was basically using the acoustic emission sensor, acoustic emission coupler, and just the high-speed data acquisition system of the ELSYS. The other one was using the sensor, the 8152, and the acoustic amp from ELSYS. And then the next one is basically just using the sensor directly coupled into the data acquisition system. And when you say, geez, can you do that? Yeah, you can absolutely do that. The data acquisition system has a high enough compliance voltage, 4 milliamps of constant current supply, and what makes it all work is it's very high speed, very high bandwidth. So it's not like a traditional channel that you would have in accelerometers. You couldn't use that channel if you had a signal conditioner or a data acquisition system that was used for accelerometers. I would tell you, I'm pretty certain it wouldn't be applicable to an acoustic emission sensor. So then we looked at several scenarios. We mounted the sensor on the metal plate with a ELSYS coupler, and this case we used the direct coupling of the sensor into the data acquisition system itself. So you look at this time domain signals, you go, okay, Bill, what does this tell me? It tells you absolutely nothing. Time domain is really not too exciting for me. So they basically all look the same. All three scenarios I mentioned, and you could look at them and say, yeah, they look about the same, and yeah, for everything I could see, I say, yeah, that's absolutely correct. But then if you do a frequency domain analysis, you see some interesting information. The Kistler coupler at a 50 kilohertz low end, and you can see here that it basically attenuates everything out to 50 kilohertz, and you see very good fidelity of signals out from 50 kilohertz out to a megahertz, whereas this one here is the ELSYS coupler, which has a 6 kilohertz lower band, which is right around here. So you can see that coupler actually has the ability to resolve lower frequencies and still at the higher frequencies. And then going directly into the ELSYS system, you can see that your lower band is somewhere around a tenth of a hertz and up to a megahertz in frequency. So you can absolutely see differences in the signal using different measuring chains. And what you need is really something that's application driven. So sometimes going directly into the data acquisition system is absolutely fine. In other cases, you may want to go through an intermediate coupler because it gives you some flexibility in performing your analysis. So again, all those things, you talk to your favorite application engineer, and you're going to absolutely get some meaningful answers to help guide your analysis. So just getting into some applications, I just want to talk a little about cavitation. And cavitation, I guess, is forming and imploding of vapor bubbles. I mean, you often see bubbly water with a propeller going through the water, and that can be very much a visual indication of cavitation. So, what happens is these imploding bubbles are actually fairly high frequency and high pressure peaks, and they could be very harsh on materials over time. So detecting cavitation actually gives you the ability to make some assessments as to, say, the integrity of various rotating equipment, for example. So cavitation measurement is a very big field, and we're not going to cover it in this session here, but just to give you just a perspective, okay? there's a lot of causes of cavitation. Certainly hydraulic parameters, how flow and velocity and pressures affect things. How does the geometric parameters operate? What is the vessel? Is it a small vessel, large vessel? What are the liquid properties? Is it water? Is it gas? Is it a mixture? What type of characteristics are occurring? Is it bubble formation? Is it vibration? Is it erosion damages? Is it pressure pulses? And then there are many methods you can use to investigate. Maybe put a pressure sensor in there and determine what's going on in the pressure range. Well, to do that, you have to drill and tap a hole and basically have the pressure sensor exposed to the flow. That again, you could use an acoustic emission sensor, which is on the outside of the structure, measuring the actual event as well. So that some options there in terms of how you want to explore. Using both is not uncommon. Using a vibration sensor, using a pressure sensor, using an acoustic emission sensor might all be used at various stages of the event anyway. So there's several options there, and certainly when it comes to pressure, acceleration, and acoustic emission, like I said, there's a lot of choices. And you talk to your favorite application engineer if those are of interest. But a lot of times the acoustic emission, because it's located on the outside of the structure, is really one of the first choices, because you have basically a unique condition. It's just mounted on the outside of the structure. So a lot of times water turbines are an area that are of interest, because you obviously have a rotating turbine here with blades, and that's going to vary at certain speeds based upon the flow through the vessel here. And then typical applications would be to try to detect cavitation happening in this environment where you have this big shaft, you have a stator, and then you actually have a motor generator set there, if you will, generating the electrical power. I won't go through this in detail, but USBR is the U.S. Bureau of Reclamation. They've done a lot of I'd say pioneering work on investigating cavitation with water turbines and dams and hydropower, and certainly putting accelerometers on the shaft and acoustic emissions on the shaft, as well as other stationary locations throughout, whether it be the draft tube lining or wicket gate stem or the bearing head cover. There are many mounting locations associated with that application. And again, what you see here is really an example of what the time domain signal might look like, where you see a impulsive, okay, I don't know why I'm getting that, and you see a frequency domain representation of it. So a lot of times, the accelerometer might pick up criteria or signals that maybe the acoustic emission and vice versa. So having two measurands sometimes is a useful method as well. What does this say here? Okay. So anyway, the cavitation produces the broadband high frequency noise that I referred to. It's often a spatially unsteady process, so there's a lot of investigation into that. It's really not a homogeneous type of event. And certainly, as I said, accelerometers are going to be mounted not only, maybe at the shaft, and or accelerometers and AE sensors are measured at the shaft and other stationary locations. And certainly part of the investigation with the USBR was they were looking at using of ways of injecting air or changing flow in terms of mitigating some of the cavitation environments. So, and that's really a pragmatic approach, because if you could mitigate that without losing, say, the ability to generate power, then you have a viable means to extend the life of your rotating equipment. This is just an example of what it might look like. I mean, you've got several different bands, if you will, over frequency. You might have a K1, K2, K3 zones of cavitation where, the red zone, the K3, is where you really have to, derate the life of the rotor blades, for example. And at K1, maybe it's a very low level cavitation that you have extreme life. So, segmenting the events over time into these categories allow you to apply an algorithm to determine what type of maintenance intervals will you need to maintain your water turbine. Also, with pumps and valves, AE sensors are used. In this case, we were really looking at the AE sensors on the test pump for this closed system. And this is an example of a spectrograph. You can see here certain, what it does. It gives you time and frequency domain. And the amplitudes are really dictating. Red is obviously the high strength or higher amplitude, where blue would be lower. And what you see here is events where the valve's closing, the valve's almost closed here, and so forth. And with the valve opening, you could see these events clearly in the spectrograms. And from that tells you a lot about the operation of the equipment. And again, this is all being done in a high vibratory environment. So what you're getting here is a measurand that's basically insensitive to vibration. In cutting force is an area, like I said, it spans many, many industries, from automotive to aerospace to university, R&D, and all just basic materials research as well. And in this case here with a lathe, we mounted an acoustic emission sensor, adjacent to the lathe, and also a force sensor, a 3-component force sensor under the turret body. And what we wanted to do there is just give an indication, hey, what does the AE sensor show in terms of its measurand, and what could a force sensor basically show? What you see here in A and B, you see that the AE sensor is picking up chipping, whereas you don't really see anything substantial here in the force signal. But when a tool breaks, you see a tremendous drop off of force. So that would definitely be an indicator too. But you can see here, under chipping concerns, you can easily use AE to detect events that are insensitive to force sensors, basically. In C and D, you're basically looking at interference cuts. And with an AE sensor, you might have a situation here where you have a tool breakage in this event. And here you'll see in the force sensor, you can see interrupted cuts where you're basically cutting through holes, if you will. And you could see a drop off and then a increase of signal strength or force, which is what you would expect. If you go through a void in the material, you're going to have a drop off of force. As you pick up the material on the other side of the void, you're going to get an increase of that. And if you have those, several of those in the material, you're going to see a periodic event like that. So again, both force and acoustic emissions show different things. So it shows you the viability of the acoustic emission measurand anyway, to give indications of the process that a force sensor can't do. This is one where it's actually a valve leakage detection, experiment, done with hypercompressors in the oil and gas petrochemical industry. And what you see here is basically you can see this suction, and this is again a high vibratory environment. You can see the high suction of the valve and the mechanical shock, and you can see the incipient gas leakage here at this phase of the process as well. So it really gives you an indication straight away, that a leakage is occurring, and then the valves need to be maintained. This one here is another high pressure valve. This is basically on this application was out at a oil drilling platform where the scientist basically built an adapter that fit around huge I'll say hex nuts, and then mounted the acoustic emission sensor right on this. And so there was a very high mechanical coupling between the clamp and the bolt. And what you see here is that you see that under leakage scenarios, you could see a peaking up of the 30 to 200 kilohertz band of frequencies, and that's clearly definable. So this investigation absolutely proved that acoustic emission is a viable measurand in a high vibratory environment to detect these types of leakage conditions. Another pipeline, a pipe leakage detection. Here, in this case, there were three sensors, AE1, AE2, and AE3. And here you had basically a leak occurring, and you had waves propagating in each section of the piping. So what you see here is the acoustic emission average signal level, where sensor 1 had a higher signal strength, and sensor 1 is like right here, which is closest, really closest to the leakage event, whereas sensor 3 was furthest away, and sensor 2 is probably somewhere about the same distance away. So you could see that the closest sensor had the highest signal strength, giving you an indication anyway that that leakage can be to be measured reliably. In another storage tank event, you put acoustic emission sensors around the tank, and you can measure, say it's from an environmental safety perspective, tanks of oil or gas, leaking would be hazardous to the environment. So having the means of detecting that, is absolutely environmentally conscious. This is one process monitoring with the press fits, where you have a plastic part and you're pressing in a metal rod. And in this case here, you can clearly see this crack occurring here with this metal piece. And if you look at this is, say, a normal scenario where you could see the press fit is well within the pass-fail criteria of this box, whereas, and also the second box too. But you see in this case here, the press fit well exceeds the pass-fail criteria of this box for indicating that some fault occurred. So that's a bad part would be detected. So wrapping it up, I think what we did here was really try to introduce acoustic emission as a viable measurand. Really be vibration insensitive, but really provide a means of characterizing complex equipment operation, and really come out with definable and reliable detection criteria that could be applied in a condition monitoring preventative maintenance perspective. Obviously, the sensor is well proven. It's been out in the industry for quite some years, and yeah, it's fully industrialized and able to stand up to the industrial environments. And certainly, as I mentioned before, the whole motivation for this is to really, investigate AE sensors in addition to other measurands you might be interested in. Really to provide another measurand for your condition monitoring process, but also effectively allows you to have the means of asset management, saving money, and having good coherent maintenance planning, so you never have a catastrophic failure, taking down the system with all the exorbitant costs involved with that. At that point, Pascal, I'd like to throw it back to you. And
yes, many thanks to you, Bill. So it was loaded with information, and I would like to hand over all the good feedback from the chat to you, from the audience. We definitely learned a lot, but we also got some really interesting questions. So let's see if we can challenge you. So the first one is about the waveguide. Is there a rule of thumb how long and or thick it can be?
I wouldn't say there's a rule of thumb, but generally they're not long, okay, in terms of it's really going to relate to the amount of temperature you have at the surface of where the waveguide is mounted, and the temperature range of the sensor. So typically a 6 to 8 inches would be enough for say 6 inches would be enough for this sensor at 165 C, and say you had a few hundred degrees C surface, that would be acceptable. Typically, the diameter tends to be more circular or rectangular. Both do work, and you want to mount the sensor right at the top of that waveguide. But there's a art and a science to it. But yeah, I don't have any simple rules of thumb for you, but I do have if you get in touch with Pascal, I think we can refer you to some papers that could potentially help you with some of your decisions that can give you some guidelines.
Yeah, for sure we can do that. The next question is also related to the waveguide. The question is, what is the best way to attach the waveguide to the unit on the test?
Weld it. That's the best way. But a lot of times that might not be possible. So yeah, screwing it in is less desirable. And, again, air gaps and lack of mechanical coupling will degrade AE. What I suggest is that you make an experiment, and a couple empirical tests, where you have a weld, you have maybe other methods that are allowable. I've been in applications where they say, no, you can't weld and you can't drill, and sometimes it's glue, so it's not really too flexible sometimes. So in my opinion, what has to be done in those scenarios is an empirical test where you try different tests, and maybe you do a pencil break test on each one and assess the signal at the sensor. It's a real repeatable test. Doesn't cost a ton of money, and could be very meaningful to your decisions.
Yeah, you already answered the first part of the next question. So
Gosh,
if I can glue acoustic emission sensor to a unit on the test,
no.
and the other one is it also possible to take duct tape to fix it, for example, to a pipe?
Well, what's important is that you need to preload. You need to make sure there's enough preload of the diaphragm at the bottom. So if your duct tape can do that, I'd say it's viable. Yeah, I don't want anything on the bottom of the sensor, but you also have to have a relatively flat portion of the pipe. So hopefully it's a large OD pipe that you can mount it to. But yeah, I think that's a possibility. But again, what's the holding strength of tape, and is it going to really apply enough force? Would have to be investigated.
Okay, good. And then there was one guy asking about the time domain. So don't we use the time domain to guess the position of the crack from the delay?
Well, yeah, time domain processing. Say you had multiple sensors. So, and if you wanted to detect a crack, say a localization of the crack, and you had, say, 3 or 5 sensors, then yeah, detecting what the leading edge of the event is, in the time domain would absolutely be the right approach. And then then using an algorithm based upon that if you had multiple sensors. Yeah, absolutely. So time domain would enable you to do that for sure.
And then let's jump to the last question. So what is the travel distance of these waves, and are there any limitations?
Yeah, there are limitations, but I don't have a rule of thumb for you, but I think within, say a few meters of distances is probably what I would use as a guideline right now.
Good. Many thanks, Bill. So once again, we really appreciated that you joined this webinar. As already mentioned before, it was recorded, so we will share the recording with you. We'll also send out your questions with the answers and also the slides. So, and if you have any questions, then reach out to your favorite application engineer. And with that, we thank you a lot, and hopefully to see you in the next session. Bye-bye,
Great.
guys. Take care.
Take care.